Very good evening to all of you. Welcome you guys. Welcome you all. So welcome. So we have one great announcement from Unacademy. So we are starting the new batches for the GATE 2024. Here you can find the top educators. You can find the top educators will take the classes, and you have a great features. And so these are the new batches are starting from the December 21st onwards. You can go and enroll for these courses, and you have a great experience you have. And these are the new batches. You can see here these batches for GATE and PSUs for 2024 and 2025 के लिए. These are the batches you can see here now, and you can plan your Unacademy subscription with a less price. So here you can able to save up to 50% discount. You can able to save. Have a look at here. And we are starting the new batches for the it's a combination of GATE and IRMS. You can find the top educators who will take the classes. You can have a look at here. And these are the new batches we are starting for only exclusively for IRMS के लिए. You can have a look at here, and you can plan this Unacademy. So All India combat test. With this combat, you can have a real GATE experience. Right. Chalo, let's continue our discussions. In the last class, we have discussed about the potential inside the conductor. And the last class, we have discussed about all the properties of a isolated conductor. Tell me now here, a properties में कोई doubt हुआ तो बोलिए. The properties of isolated conductor under electrostatic equilibrium conditions. So here, the first one, the most important thing what you observed here, the net electric field inside a conductor is 0. There is no electric field inside a conductor. And the net charge inside a conductor is how much, you tell me? 0. And whatever the charges we have given to the conductor, the charge will lies completely on the surface of a conductor. Charge cannot penetrate into the conductors. And the electric field at any point on the surface of a conductor is how it is, which is normal to the conductor surface. And conductor is a equipotential surface. And this thing we have discussed, and all of you tell me. This thing we have discussed, right? चलिए, let's continue now here. अगर कोई doubt हुआ तो in the previous classes let me know. And if you have any queries in the previous classes, please let me know. So then, नहीं तो here हम आगे बढ़ेगा. Shall we move forward? Tell me all of you. Right? Now, so I hope you might understand this thing here. So let us get a more clarity on this thing here. Let's get a more clarity on this thing. So here let us have a more clarity on this topic. What topic I want to repeat here? This thing now. Okay, fine. Look at now here. Now see this thing here. This is my conductor. Now the radius of the conductor is capital R. Radius of this conductor is capital R, and this is what type of conductor, you tell me? Solid conductor. This is what? Solid conductor. So you can see now here in this conductor, so the potential is same at every point. Potential is same every point. Radius of the sphere is capital R. Let us say I want to find the potential at this point, and this point is at a distance of small r. This point is at a distance of smaller from the center. So what is this distance is, you tell me now here, which is equal to small r. Now you see this thing here. So I want to find the potential at the A. Where is a point A? Tell me. Where is a point A lies? You tell me. Inside the sphere or outside the sphere? Where is a point A lies? You tell me. Inside the sphere or outside the sphere? Where is a point P now here? Inside the sphere or outside? Inside. So then the potential at point A, which is given as, So for any formula we have kq, 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 you tell me now here. Now you tell me now here. So here the distance, this distance is how much, you tell me, smaller. This distance is smaller. Radius of the sphere is capital R. इस दोनों में which is बड़ा, which is more value, tell me, which is bigger value, tell me now here. Small r is bigger or r is bigger, you tell me. Whether small r is bigger or capital R is bigger, you tell me. Capital R. So that's why in the denominator you can write capital R. That's all. Capital R value bada hai. So then write the capital R. Okay. Next. Here this will have charge Q here. Now let us consider, I want to find the potential at this point B. Now this distance I am calling this thing as a R. This distance is smaller. Now you tell me now, I want the potential at the point B, which is given as what we can say KQ by, now you tell me now here, with for this point B the distance is smaller and the radius is capital R. For this point B, you tell me which is bigger value, small r is bigger or capital R is bigger. Is bigger value. So here whichever is bigger, that you write simply. Small r is bigger na, that value you can write. That's all. इसमें ज़्यादा सोचने के बात नहीं है. So here whichever is a bigger value, that you can write simply. Okay. Right, all of you. Now let's have a more clarity on this thing here. So देखो इधर, let us consider we have a concentric spherical shells. Let us say we have two spheres we have. So this sphere having the radius, I am calling this thing as a RA, and the second sphere radius I am calling this thing as a RB. That is a property, right? So here this the radius of the inner charge is RA we have taken, and the inner sphere having a charge of QA. Outer sphere charge is what, you tell me, QB. Inner sphere charge is QA, outer sphere charge is QB. Now this point I am calling the inner sphere, this point is calling as a B, and this point I am calling this thing A, and B I am calling. Now I want to find the potential at the point A and potential at the point B. Okay. Now all of you listen carefully. I want the potential at the point A, that I am calling it as VA. The potential at the point A, which is the VA. The potential at the point A, which is because of what, you tell me, the charge because of the first sphere as well as the charge due to second sphere. Hana boliye. Potential at the point A, which is given as due to the first sphere as well as the second sphere. Now let us find the potential at the point A because of the first sphere. First sphere, tell me what is the potential here, and which is given as K into charge of the first sphere is QA by, listen carefully, I want to find the potential where, you tell me, at the point A. Now you see this thing here, that means this distance is RA, QA charge distance is RA, and radius of this sphere is also RA. So here which is a bigger value, tell me? So this distance we are calling it as RA, and so here this radius of this sphere radius charge, you tell me how, which is a bigger value? Which is a bigger value, tell me? Which is a bigger value, tell me now here? नहीं आया बोलिए. Listen here. Now I want to find the potential. Now you have to see the, I am talking about what type of charge. I am talking about the QA charge. We are finding the potential because of the QA. So you see the QA sphere radius only. QA sphere radius and distance you need to compare. This is the QA sphere radius is a RA, and so this means I have to find the potential at this point only. At this point, this radius of the sphere and this potential on this point A both are same or not? Both values same now. Then what has to be taken? You tell me now here, which is equal to RA. Is it fine, all of you? Wherever you want to find the potential and the RA, both values are equal, so that's why you can write RA is fine now. Now plus, now I need the potential because of the second charge, second sphere charge, that is QB. Tell me what I can write now here, that is K QB, second charge now here KQ by. Now you tell me, I want to find the potential where, you tell me, at the point A, because of this QB now, because of QB. Now you tell me now here, so from यहाँ से यहाँ तक distance we have, so यहाँ से यहाँ तक distance we have. Now you tell me now what is the radius of the second charge, now tell me. Radius of the second charge is how much, you tell me, RB. Now you tell me now here, which is a bigger value, tell me. Which is a bigger value, tell me now here. So this distance is R. Now here, so this I want to find here. So that means that has to be written RB. Is this point clear, you tell me. ये सभी को आया कि नहीं बोलो. ये सभी को आया कि नहीं बोलो. ऑल ऑफ यू सभी ने कमेंट करना पड़ेगा ये बात क्लियर हुआ कि नहीं. अगर ये बात क्लियर हुआ तो तभी हम आगे बढ़ने वाला. इज दिस पॉइंट क्लियर, टेल मी ऑल ऑफ यू. चलो, नाउ आई वांट टू फाइंड द पोटेंशियल एट द पॉइंट बी आल्सो. I want to find the potential at the point B. I want to find the potential at the point B. The potential at the point B, which is because of what, you tell me. The potential at the point B, that is because of the potential due to the QA as well as potential due to the QB. Both potentials we need to find out. Yes or no, tell me. So the potential because of both we need to find out here. Isn't it, all of you, tell me. Now let us find the potential because of the QA and QB, both we are going to see. Now tell me now here, for because of the first charge, tell me potential, tell me. I can write this thing as KQA by, tell me now what I should write here, tell me what I should write now. I want to find the potential at this point B, and this is now here यहाँ से यहाँ तक means this is nothing but radius of the second sphere na B. Now which is a greater value, tell me now here, RB. So I can write RB, tell me. Now tell me now potential because of what, you tell me now, second charge I should consider. That means because of the Q2, tell me what I can say, K QB by what I can say now, tell me, which is equal to RB. हाँ ना बोलिए this thing. Anna बोलिए this thing here. Is this point clear to everybody? सभी को ये बात क्लियर हुआ कि नहीं, बोलिए. चलो हम आगे बढ़ेगा. चलो, that's all. So this point you understood now here. So let us move little more here for more clarity. Agar, so here now you tell me now here, I have taken the for more complex case to get a more command, we are going this thing here. So that's what I told you. So this is now here, I'm calling this thing as RA, this is RB, and this is RC. And the charge we are calling this as QA, this is the QB, and this is the QC. Now you tell me now here, this is inner sphere, this is my A, and this is my B, this is my C. We have three charges, we have three spheres we have. I want to find the potential at point A. I want to find. Tell me now here. The potential at the point A, which is because of the potential caused by all the three charges. Tell me now what we can say here. Charge 1, which is given as KQA by RA, plus, tell me now here, because second charge, how to write, you tell me now here, KQB by what I can say now here, RB, KQB by RB. Next, KQC by RC. Is this point clear to all of you? Now tell me now here, potential because of the second sphere at the point B. Tell me now here, at the point B, I need the potential because of all the three charges. Tell me which is given as KQA by what I can say now here, RA, RB, RC. What I should write? What I need to write? I want the potential at the point B I want. So tell me now what I should write. Yes, what I should write now, tell me. RA, RB, RC. So which is given as RB, right? Now tell me now KQB by what I can write now here, RB. Next tell me now here, KQC by what I should write now, tell me. What I should write now, potential at the point C because of the three charges, which is given as what I can say. So what I should write now here, RA, RB, RC. So what I should write now, tell me now. RA, RB, RC, which is given as RC. Isn't it, all of you? Tell me. Now tell me now, potential at the point C means outer sphere, which is given as what I can say, KQA by RC plus KQB by RC plus KQC by RC. So बोलिए ना भैया, ये सब कुछ आपको समझ में आया कि नहीं, मैंने कैसे लिखा? So this is conductor is a equipotential surface. The potential at any point, which is what should be, it is like this. Is it fine, all of you? बोलिए. चलो हम आगे बढ़ेगा, बोलिए. Done? Chalo. That's what we have discussed in all of you. Right, now you take this problem here, all of you. Take this problem. Consider the following statement associated with the basic electrostatic properties of an ideal conductor. Tell me now, which are the following statements are correct? Tell me first property. The resultant electric field inside the conductor is zero. Hana boliye. Inside the conductor, resultant electric field is zero. So this statement is correct. The net charge density in the interior is zero. There is no charge inside. Inside we don't have any charges. The net charge resides on the surface of a conductor. Hana boliye. And the surface is a always equipotential surface. Yes. The electric field just outside is zero. That we can't say here. Electric field may not be zero. but the conductor must be equipotential surface. कौन सा option tell me now here? Option A. बोलिए this thing. Right. Yeah, take this problem. Take this problem. Two spherical conductors, the radius given as RA and RB, and RA greater than RB they mention, having a charge of QA and QB on its surfaces. The two conducting spheres are connected by a long conducting wire. These are connected by a long conducting wire. Then find the charge, electric field and potential on the surface of the conductor after the interconnections. Right? Now, see this thing here. I have a two spherical conductors we have. The two spherical conductors we have like this, having the radius. So here this radius which is given as a RA, and this radius which is a RB, and this having a charge of how much we can say QA, and this have a charge of QB. Right. Now, so here the two conducting spheres are connected by a long conducting wire. These two are connected by some conducting wire. They are connected like this. Right. Now before the connection, if I call the total charge in this conductor, if I call this as a QT, if I say, which is given as what I can say here, QA plus QB. Ana boliye. Before the connection, the total charge which is given as what I can say here, QA plus QB. Total charge. Right. Now, after the connection, so here see this thing, what's going to happen, you tell me. When we have connected the charges, then see what's going to happen. If I call this potential of the first sphere is VA and potential of the second sphere is VB. Now can you tell me the potential of the first sphere VA, what I can call this is now here K into QA by RA. Potential of the second sphere VB, which is given as K into QB by RB. All of you tell me. This is the potential on the second sphere. Now if you see carefully, now these are the charges and the potential on the two spheres before the connection. Once they have connected, what happened, you tell me. Once those are connected, now this complete combination will behave like a single conductor only, na? Single conductor. If it is single conductor, what happens now here? Potential same hona padega. Conductor must be equipotential surface, so potential must be equal hona padega. That means what I can say here, VA must be equal to VB. Ana boliye. So that means when you have connected the two spheres connected, then what's going to happen now here? Charge will start flowing from one conducting sphere to other conducting sphere until both will reaches to the equal potential. The charge will start flowing from one to other until the potential must be equal. Hana boliye. Now here this QA, QB are the charges before the interconnection. Now after the interconnection also, can I say same charge will lies. same, it may not lie the same charges. Some charges will flow from one to other now here. Then as a result, so what I can say now here, potential, if I call after the connection, this will having a charge of Q1, this will having a charge of Q2. Right, so then what happens now, but the total charge we can say Q1 plus Q2, that must be equal to QA plus QB. Charge is law of conservation of charges. Charge neither be created nor be destroyed. So that means when you have connected these two conducting spheres, some charge will flow from one to other, either QA, so first to RA, QA to QB or QB to QA, we don't know, but the total some charge, it may not be equal. Somehow the charge will flow from one conducting sphere to other conducting sphere. So I can say if this charging is a Q1, I can say Q1, and this I can say Q2, I can say the two potential must be same. So tell me what happens now here, that is K Q1 by RA, and which is equal to K into Q2 by RB. all of you boliye, the potential will become like this. Now what we can write now here, this is Q1 by Q2, Q1 by Q2, which is given as what I can say, this ratio, which is given as RA by RB. all of you boliye, that means the charges will divide in this ratio, will divide. If I know the Q1 by Q2, which is equal to RA by RB, and we know the relations, you see here Q1 by Q2, the ratio of the charges which is given as RA by RB, and what else we have seen now here, Q1 plus Q2, which is equal to QT. From this, can you apply the division rule? Division rule, from this we can get this Q1, which is given as what we can say, charge of Q1 directly proportional to RA, radius. So I can write this thing as RA by RA plus RB into total charge, I can say QT. Next Q2, which is given as RB by RA plus RB into total charge QT. all of you boliye. So these are the, what are the Q1, Q2, these are the charges present on the spheres after the interconnections, after the interconnection. Now what else they asking to find, you tell me. They are asking to find the charge as well as electric field also we need to find now. Yeah, you tell me now what is the electric field now here. E1 if I say, which is given as 1 by 4 pi epsilon into what we can say, this is Q1 by, I can say this is R1 square, I can write now RA square, 1 by what we can say now here, RA square. Now if you see carefully, Q1 by RA, we have the relation now, tell me. So from this I can get this thing as 1 by 4 pi epsilon into Q1 by RA, which will get it as a QT by, I can say this is RA into RA plus RB hoga na, tell me. Next E2, which is given as 1 by 4 pi epsilon into what I can say here, Q2 by RB square, which is given as 1 by 4 pi epsilon into what I can say now here, Q2 by QT by RB into RA plus RB. all of you boliye. So we have the electric field like this, isn't it? Next, whatever the potential, tell me, V1 first sphere potential, which is given as, that is 1 by 4 pi epsilon into what I can say here, Q1 by RA, and this Q1 by RA if you have, will get it as 1 by 4 pi epsilon into what I will get, you tell me, qt by what I will get now here, that is RA plus RB. Tell me all of you. Next V2, which is given as 1 by 4 pi epsilon Q2 by RB, which is given as 1 by 4 pi epsilon into what I will get now here, Q2 by RA plus RB. You can observe carefully here. So the V1, V2 both are equal, you see. If we observe carefully, V1, V2 both are equal, isn't it? So after the connection of the two spheres, obviously the two conductors will behave like a single conductor. So then the potential to same hoga na. So that's why. Is it fine, all of you? Okay. Yes. Now if you observe carefully, if I observe here, so this is what here? Here what we have, this is. Now here this is Q1 by RA. So this is Q1 and we have RA will be taken to this side. Then what we are left out here? Q2 by denominator we have RA plus RB na. Denominator we have RA plus RB, isn't it? So like that. So this is like what we can say now here. Like here, if we have a resistor in your networks, we used to write the voltage division, we can write now. For resistor, so if I call this resistor is R1, this resistor is R2, this total supply voltage is a Vs if I say, and this voltage I am calling this thing as a V1, and this voltage I am calling this as a V2. Now you tell me now here where V1 plus V2, V1 plus V2 which is equal to Vs, and you can see V1 by V2 which is given as what, you tell me, R1 by R2 now. So that means then what we can say, V1 which is given as what? So this voltage of V1 which is directly proportional to R1 na? So then we can write this as R1 by R1 plus R2 into total voltage, we can write or not, isn't it? So that is V2 which is given as V2 proportional to R2. So that's why R2 is a numerator. R2 by R1 plus R2 into total supply voltage we can write now. So that manner I have written this equation. Here you can see now here Q1 by Q2 is proposed given as RA by RB, and Q1 plus Q2 is equal to QT now. So charge of Q1 is directly proportional to RA. So that's why Q1 is equal to RA by RA plus RB into total charge. Is it fine, all of you? Right. Now अगर आपने ध्यान से ऑब्जर्व किया तो here they given in the problem, if you see in the problem they given, what they given, you see this thing here, they has mentioned that RA greater than RB, they has mentioned RA greater than RB, they has mentioned. If you see carefully, now in this Q1 and Q2, you tell me now who charges more? Charge is more. If RA greater than RB in this Q1 and Q2, who charges more, you tell me? So that means Q1 charges more compared to Q2, tell me. Q1 charges more compared to Q2. Hana boliye. And now you see this thing. In this electric field E1 and E2, whose electric field is more? Whose electric field is more, you tell me. Electric field is more here, and here you see this thing RA value greater. Here RA we have in the denominator is there, so that means E1 is smaller compared to E2. So I can write this as E1 is less than E2. Tell me. E1 is less than E2. Hana boliye, check it now here. Here which is higher value, RA value greater. Here except RA RB remaining everything is same only na. So here RA is there. So since RA value greater, so E1 value smaller compared to E2. Next, what about the potential, you tell me? And what about the potentials, you tell me? Potential, which is both potentials are equal, you see carefully. V1 which is equal to V2. V1 equal to V2, you see this thing here. Both potentials are equal. See this thing, that's a beauty. अगर आपने ध्यान से देखा तो generally what we expect now here, whichever the charge we have, so the charge is high, so that electric field is high, but it won't be like this. In case of conductor, that property does not satisfy. Isn't it, all of you tell me? Now here, if we observe carefully, why the electric field of E1 is less than E2? Why the electric field of E1 is less than E2, you tell me? Why it is E1 less than E2? Because first sphere radius is high. Because first sphere radius is high, that's why electric field is small. That's why electric field is small. That means if the radius is high, electric field is less. If the radius is high, electric field is less. Can you conclude this thing? Tell me. Now let's consider we have a situation like this, and so we have this thing we have. Let us consider here. Now this will have an electric field which I am calling this as E1, and this electric field is E2. Tell me whose electric field is high, you tell me. Whose electric field is high, E1 or E2? So E2, so EB is high compared to E1, tell me. So this electric field is high compared to EA. Now what I am doing is, here I made by but I made the scenario this conductor. What I made, here I have this conductor as like this. I have connected this conductor like this. I made this conductor like this. Let us consider. I made this conductor, I made like this. Now here, where we have high electric field, tell me, at the EA location, EB location. Where we have high electric field, you tell me, at which location electric field is high? So here EB location electric field is high now. So for your, and what I am doing is, this is also conductor. I have conducted. So here I made this thing is very steeper, very narrow. I did here. You can see, have a look at here. So what I did now here, this part I made this thing as like this. For your more clarity, so electrical fellows have a very good application on this concept. I design this conductor like this. Like this. Okay. I made this thing here. Now you tell me now here, this I am calling this as a EB. Where we have high electric field, you tell me now here, EA or EB. So which field is high, you tell me. EB is higher now. since because at this is, if you see carefully at this location, it is very sharp now here. Now, so means what we can say, at the sharp locations, the electric field is high, I can say. At the sharp locations, electric field is high compared to smooth locations. Hana boliye, here we have a smooth we have. So electric field is high at the sharp location compared to smooth location. As a result, so the sharp location can able to ionize the things, ionize the air particle also. Because of that, we have a corona discharge. Will occurs at the sharp locations. We have a corona discharge will occur at the sharp locations compared to smooth locations. Hana boliye. Corona discharge will occur at the sharp locations. It can able to ionize the air particles. It can provide some discharging path. It will provide some short circuit path can able to establish. So that is a one of the it. Because of this is we need to design the things such that, so here corona discharge to occur. Corona discharge is advantage or disadvantage? Corona discharge is an advantage or disadvantage? Yes. Exactly. So that's why it is one of the disadvantage factor. So that's why, so we need to take care of that one. We cannot, so here, and we cannot have a discharge. And where it is an advantage now here, and doing the lightning conductor. You might heard at the top of a building we used to install one lightning conductor. At the top of a conductor, which is a very smooth, they will move. Because of the smooth, now at that location we have electric field is high. Then it can able to provide a discharge path for the lightning. So as a result, the lightning coming from the sky can able to go in this via this conductor, lightning conductor. Hana boliye. That is the one of the advantage lightning conductor concept. Isn't it, all of you? Fine. Chalo. Now let us see the electric field and potential for the different type of charges. Electric field and potential to different type of charges. Due to different type of charges. Electric field and potential due to different type of charges. The first one we are talking about the point charges. So for the point charges, हम पहले भी we know I think so already. Electric field and for due to the point charges. The electric field due to a point charges, which is given as what? That is KQ by R square. KQ by R square into AR cap with the units of volts per meter. The electric field due to point charge is given as KQ by R square. And the potential is a scalar quantity which is given as what? KQ by R with the units of volts. Potential due to a point charges which is given as KQ by R. Okay. line charge. Line charge. The potential and electric field and potential due to line charges is. Now consider we have taken this is my x-axis and y-axis and this is my z-axis. And consider we have a line charge which is along the z directions. We have a line charge and this is the infinite line charge having the charge density which is ρl coulombs per meter. Line charge density ρl coulombs per meter. Due to this line charge, let us say that I want to find the electric field at the point P. At the point P I want to find the coordinates of the point P is something x comma y comma z. X comma y comma z. To find the electric field at the point P because of this point charges, what you need to do here, draw one perpendicular line from point to the conductor. Draw one perpendicular line from point to the conductor. Now, so can you tell me coordinates of this point here? 0 comma, this point lies on z axis now here. So we can say 0 comma 0 comma z. Now, so find the distance between these two. Here we are finding the electric field where? At the point P. Wherever you want to find the electric field, that point is a final point. So this my arrow should be always towards the final point. This distance I am calling it as a rho. This distance I am calling it as what? Rho. So then the electric field at the point P, which is given as E equal to rho L by 2 pi epsilon that is mod rho into aero cap. Rho L by 2 pi epsilon mod rho into aero cap. Now, what is this thing here? What is this rho L value? Rho L is a line charge density. What is this rho L is a? Rho L is a line charge density. So this is, we have derivations we have. So here for the GATE point of view, the derivations are not required and focus on the results only. Concentrate on the results only. Right. Next, what is rho is a? Where rho is a distance vector. Rho is what? Distance vector. Rho is a distance vector. From the, yes, now here like this distance vector. Distance means final point minus initial point. And what is this aero cap, you tell me? Which is a unit vector. Unit vector, which is given as what? How to get a unit vector? That is given as rho bar by modulus of rho. Rho bar by modulus of rho. That is a unit vector. Rho bar by modulus of rho. Fine, all of you. Where rho L is a line charge density and rho is a distance vector and aero cap is a unit vector. Fine. Now here if you observe one carefully, if you see carefully, at this point P, I want to find my electric field. What I did now, I have drawn one perpendicular line to this line charge. Here the line charge is along the z-axis. That's why I have drawn the perpendicular line to z-axis. Agar the line charge is along x-axis, we should draw the perpendicular line to x-axis. The line charge is along y-axis, we should draw perpendicular to y-axis. Wherever we have a line charge, so we should draw the perpendicular, we should draw correspondingly, we should draw perpendicular. Done? Yes. You can take this problem, all of you. A uniform line charge of Royal is given as a 10 nanocoulombs per meters. And one more thing here. So the line charge, what we have seen, this formula is valid in case of a infinite length. We are talking about what type of charge, you tell me now here. Infinite length charge. So this is, which is infinite length. Okay. Next, now we are talking about the finite length charge here. In this case, they given having the line charge density is given as a 10 nanocoulombs per meters, lies along x-axis from how much is length, you see this thing, 4 to 10 meters. Now they are asking to find the electric field at the origin. Means, let us say this thing, this is my x-axis, here this is my origin, and I have a line charge. Is there here like this. This is my line charge. You can have a look at now here. At this location, x value is how much? 4, and here this x value which is equal 10. This is a finite length charge now. Due to this line charge, I have to find the electric field at the point, at this origin we should find. Now tell me now here, how we can find the electric field, you tell me now here. This is the line charge. What is the electric field formula? Electric field formula, which is given as, what we can say here, that is kq by r square. Let us focus on the magnitude. But lekin, the formula what we have seen, this formula is for what type of charges? Only for the point charges only. What type of charges is it? This formula is for only for point charges. Now, so what I need to do here, I am taking a small part, I have taken here, small part in this conductor, and this is having a small length. I am calling this length as a something small length which is equal dx. Small length is calling as a dx, and this small length will have some charge or not. The charge I am calling as dq. As we know, we'll define the charge density rho L, which is given as what we can say here, differential charge per differential length I can write now. So from this I can get my dq. I can get dq which is given as what we can say, tell me, rho L into dx. From this I can get my dq which is given as rho L into dx. Isn't it? So you see this thing, rho L is a charge density and dx is a small length. If you see carefully, if as dx value tending to 0, it is very small, then I can say dq will becomes, I can say, point charge, I can say now. What is meant by point charge means the charges having negligibly small physical dimensions. As if I have taken the dx is tending to 0, dq will become a point charge. So then I can find the electric field. Can you apply this formula to find the electric field? And the small electric field, I am calling this thing as a dA, which is given as k into dq by x square. So from this, what I can say now here, dA, which is given as k into dq, which is given as rho L into dx. And this strip, let us consider this is at a distance of x. This distance, I can call this distance, we can say x square, I can say now. All of you, this is what is the dE now. This is the electric field because of this small part of dq. Now I want to find the electric field because of the complete line charge now. For this, what I should do here, we'll integrate it. That is integral of limits are what we can say, x limits from where to where, 4 to 10, that is k into rho L dx by x square. Here you can see now here. So here now this electric field E which is given as k into rho L is a constant. Integral from x limits are from 4 to 10. I can say here dx by x square. Integrate and get the values, which is given as k into rho L. Integration minus 1 by x now here. Limits 4 to 10. Substitute now here k value. So k into rho L value given now, we can replace now rho L value how much? 10. So which we can say 10 into 10 power minus 9 into what we'll get now here. This is 1 by 4 minus 1 by 10. Minus cancel now here. So this is my electric field. Do simplify, get the answer. Where k means what we can say here, which is equal to 1 by 4 pi epsilon naught now here, which is given as 9 into 10 power 9. Okay. So now substitute the values and you can get it. Is it fine, all of you? This is what we have seen for in case of what type of charges. This is a point charges. We have seen this is the very finite line charges we have discussed. All of you tell me this thing. Done. Next. Now you see this thing. Look at now. An infinite line with uniform charge density is given as like this. They given now it is an infinite line charge having a charge density given as like this. Now they are located, this line is located at x is equal to 2 and z is equal to 4. Now due to this they are asking to find the, no, we cannot apply. So this formula we have seen this thing now. This formula which is only for infinite line, infinite length only, this formula is valid. If it is a length of a conductor is a finite length, then you need to approach this method. You have to approach. For in case finite line charge, you need to approach this method. If it is infinite line charge, you can apply. Now here you see this thing here, this infinite line charge now. Now if you see carefully where the charge is located, now tell me where the charge has been located. That is important here. If I say this is my x-axis and this is my y, I am taking, yeah, this is my x-axis and y-axis and this is my z-axis I am taking. The line charge, if you see carefully, which is located x value to z value 4, x value to z value 4, whatever the y value, that means x value fixed, z value fixed, but y value not given means what now? Then you can take the y value can be anything from minus infinite to plus infinite. Whatever the y value, tell me minus infinite to plus infinite. That means we have an infinite line charge which is parallel to what axis, you tell me? What axis now here? Parallel to y axis. So that means the infinite line charge is like this. Now if you take any point on this line, x value is always 2. Y value, it can be anything, but z value is how much, you tell me? 4. X and z values are always constant, but y can be anything from minus infinite to plus infinite. Is this point clear? First of all, tell me. But x and z will be constant. Now, so if you take any point on this thing here, if you take this point here, x value is 2, y value is something, and but z value must be 4 only. Like this. This line is parallel to what axis? Y axis. Now due to this, I want to find the electric field. Where you want to find the electric field now here? At origin. So means wherever you want to find the electric field, we need to draw one perpendicular line. We should draw now. Now I have to find the electric field here. Now what is the coordinates of this point? You tell me 0, comma 0, comma 0. Now here this, what is the y coordinate here? 0 now. Then y coordinate here, it will be exactly 0 will come. At this, wherever you want to find the electric field, at that point y coordinate is 0 now. So here 0 will come. So from this we can get the rho value. What is rho value? Which is given as, so that means final point minus initial point, which is given as minus 2 into ax minus 4 into az. All of you tell me. Now we can find the magnitude of this rho, which is given as square root of 4 plus 16. So which is equal to root 20. Now what is the electric field due to a point line charges? That is given as rho L by 2 pi epsilon mod rho into a rho cap. Now so substitute all the values now here, and how we will get the unit vector? A rho cap, which is given as vector by its magnitude will give unit vector. So that means what we can say here, minus 2ax minus 4az by magnitude we got as root 20 now. Substituted all these values, you can get it. How many days I can complete, I don't know. So here, let's see this thing here. What are the number of days we are continuing? We'll see. We can't say this thing. Substitute the values now here. They've given the values now here. Here the royal value we know, and you see this thing. How much is, as we know, 1 by 4 pi epsilon naught value, how much it is? Which is given as 9 into 10 power 9. Here we want what now here? 1 by 2 pi epsilon naught. How much this value? Take 1 to the other side, and which could be given as what we can say here, 18 into 10 power 9. This thing. Fine. Okay, so this is about the line charge electric field calculations. Yeah, that's for the today's class, and tomorrow we'll discuss about the surface charges and volume charges we'll discuss. Tomorrow we'll discuss about the surface charges and the volume charges. So all of you do start doing the problems, practicing the problems, and open the PYQs books and start doing the problems. Fine. Okay then, see you. Bye bye.